Hi, class. In our last video, we looked at diatomic elements, and those are those elements that are made of diatomic molecules. Half sprinkle. Well, now let's talk about compounds, and this is a throwback to the stuff we were doing before, and we saw in that handout we're dealing with mostly compounds, which I highlighted in blue, right, in that worksheet. So, what's our first step when we see a compound? We got to remember what a compound is. A compound, pure substance, made of two or more elements in fixed ratios. Okay. Ratio sounds mathy, but whatever. It's like, 2 to 1, 1 to 2, 3 to 2, whatever. Well, what determines that? Well, the first thing we have to figure out is what kind. Is it ionic or molecular? Okay. So we can just go, what type of compound are we dealing with here? Well, the first question we got to ask is there a metal present? And if the answer is no, only nonmetals, then you've got yourself a molecular compound. If you have a metal and a nonmetal, you got yourself an ionic compound. And the metal one is called the cation, and that's why I made the cute little cat ion, the knight. Okay, ionic compound. Okay, now let me think of one here. Just pull one out of my mind. Hmm. Let's think about this for a minute. Ionic compound, a metal. So let's pick a metal. Well, metals have positive charges. Okay, so if we get the name, here's how we name it. We're going to call this one, let's do magnesium, because we did this one before. Yeah, let's just do magnesium oxide. Magnesium oxide. I want to do group one. Let's do lithium, no, potassium oxide. Okay, that's the name. And let's do one called oxygen difluoride. Okay, so there we go. Now, the giveaway for molecular compounds in their name, you're going to see this thing. Okay, look for the Greek prefix. Di, tri, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So those are all the Greek prefixes we have to use. And the fact that we said oxygen difluoride, well, what's cool about this is that there's no mono here. Okay, we don't put mono in front of oxygen. We don't put mono in front of we don't say monocarbon monoxide. We just say carbon monoxide. So similarly here, we've got this cool chemical called oxygen difluoride. And so if I go oxygen, and there's only one of them, and then I go fluoride, so that's capital F, and then we do a little subscript there, it's called, that's OF2, right? Now, potassium oxide, what's up with that? Well, we have a couple options to figure out our ionic compounds. Now, I'm biased. I like drawing, as you can see, excuse me. And so if I'm going to do the simple particle method, watch it go. Okay, so potassium has a charge of 1. And where do we find these? Well, in that periodic table you're allowed to have. An oxide has a charge of -2 if it's an ion. And so the rule is for a formula unit, and we all know what the short form for that is, formula unit, we can just call them units, is the lowest ratio such that the charges zero out. And so in this case, we would learn that the chemical formula for potassium oxide is K2O. Now let's take a look at how this formed from atoms to ions using Lewis structures. So we just remember that potassium has 1 electron and oxygen has 6. And so if I drew one of each, I could say, well, oxygen wants to have that electron, right? And potassium, well, ostensibly wants to get rid of an electron to have a full outer shell, so it's losing an electron. But oxygen still needs another electron, which means that it would need to rip one from another potassium right there. And this process here is what we call the transition complex. So this is what's going on. Say like when magnesium was reacting with oxygen, well, oxygen starts as a molecule. It has to actually first off bust up into the atoms. And that's why we hit it with such high heat. But once it gets going and these electrons start transferring, they start driving so much energy that it just happens spontaneously. Okay. So these are atoms with the electrons going. Okay. And let me just erase this. We'll go atom. Oh yeah, atom. They're all atoms at this point. Now, again, oxygen exists as a molecule, so it's got to be ripped apart first. Okay. Well, if we look at the atoms of oxygen over here, right? Again, two electrons needed for oxygen, but fluorine is a nonmetal as well, and nonmetals want to gain. Fluorine needs to get one electron. Oxygen needs two. So fluorine says to oxygen, you know what? I'll lend you mine if you lend me yours, and this one does the same. So these are the atoms: fluorine atom, oxygen atom, atom. And right now we're in what I like to call the transition complex. Well, not I like to call it. It's called the transition complex. Okay. Now we're in the products stage. All right. So here we got ions, right? So we're going to draw a K with a square bracket around it as Lewis would. And if it's a metal, we don't draw any electrons. If it's a nonmetal, we draw all of them, all eight. One, two, three, four. And you can draw the one or ones that it gains as like little X's or even different color if you want. You don't have to. -2. But we got to remember that we have two potassium atoms involved here, don't we? Okay. And so we see a number 2 down here in what's called the subscript position. If I'm asking for, show me the Lewis structure of this compound, and I give you an ionic compound, this is the kind of thing I'm expecting. And if you look carefully, well, this is why crisscross works for ionic compound. Okay, so you're told potassium oxide, so you go like this. You just draw the element symbol like that. That's a 1, and oxygen is a 2 minus. There you go. And you crisscross and you move just the number, not the charge, right? Because that's going to give you that we need to have two plus ones to zero out 1 negative 2. And there's your chemical formula. Now, again, I'm really partial to uh, the particle drawing, okay? Because it gives you a sense that there's actually something there. That's fine, whatever. Okay, so oxygen, atom. Well, these aren't going to become atoms, this or ions. This can become molecule, right? So for that, we're just going to go like this. We'll draw our lone pairs. Two oxygen always has two. And oxygen's cool because it always only do two bonds, either two single bonds or one double bond. We see that over and over again in nature. Okay, and here's our OF2. Now let's say I want to represent this thing as a ball and stick. Okay, simple particle as we could call it. So what we do is go like that, and then draw a green circle there, a green circle there. So kind of looks like a water molecule, but it's not. All right. So that's a ball and stick for that. Or we could go full space fill here and just kind of blob them together like that. And now you see why water is a bent molecule because of those lone pairs, right? And that's important, right? Because that's what gives water its polarity, which also leads to, and the cool thing about water molecules, so there's a space fill over that guy, okay? And there we go. All right, so that's how to go from molecules to ionic compounds. All right. And we discussed for the certain metals, they have more than one charge. And if they do, then you need the Roman numerals after their name. Potassium only can be a +1. And so for potassium, we don't put a number one in front of it. Okay. Let me do another example just so that we're a bit clearer. Okay. Let me think of one. All right. Let's do iron 3 oxide. Like this is rust, actually. Well, one of the components of rust is iron 3 oxide. There's others. But the main one, the main biggie is iron 3 oxide and rust. Okay, oxide. There we go. Okay, so if I was going to do this again, uh, simple particles, we can start there. All right, so that 3 tells me to use the +3 version of iron. And oxide is always, well, it's always a -2. There's negative Nelly right there. Okay, boom, 2 minus. Okay, so again, we're going to put them together until we get a number that can cancel it out. So 3 oxides and 2 iron 3s are going to give us a total of 0 for that formula unit. Right? Now, this is not a molecule at all. Right? It's not the same thing. It's a formula unit. And if we look at this happening, watch this. This is kind of cool. So iron 3, right? We go like this, we go +3. We go oxide, we'll draw it as a Lewis structure. We go -3, and now, oh, sorry, -2. There you go. Okay, so we know then that we got 2 and 3. So 2 iron ions with 3 oxides. Okay, now what about a different example? Let's consider, hmm, let me think of another one quickly. We're going to go aluminum chloride, aluminum oxide formation. Okay, so if we start off with aluminum atom, this is going to go quick. We're going to speed run this guy. Okay, and we know there's an oxygen. So this is the atoms. We're going to form into the ions. Okay, so aluminum needs to get rid of 3 electrons and oxygen needs to gain. So this aluminum can dump 2 electrons there. Now it's got 1 extra, so that means that another oxygen, whoop, that's too thick. Another oxygen is going to be required to take that aluminum's extra electron. Watch this. That one's going to go to there. Okay, cool. Okay, fine. Now we've got another aluminum then, because that oxygen, the second oxygen, doesn't have enough electrons. It's going to need an extra electron. Now that one's happy. Okay, so that each oxygen so far has gained 2 electrons, but we look again and there's aluminum. Oops, again, too thick, sorry. Back out. There's another oxygen can come in. And where are these coming from? Well, the air, right? Just imagine like if aluminum oxidizes, which it actually does. Now, aluminum oxide is a really neat thing because when aluminum oxidizes, unlike iron oxide, it creates a protective layer. So all those airplanes and jets that are made of aluminum actually have the outside of them aluminum oxide, and so does the aluminum I gave you, and that's what the bubbles were coming off of it when we hit it with the copper 2 chloride. Okay, so we can see all these electrons going. So 2 aluminum atoms are going to give their electrons to 3 oxygen atoms, and of course, oxygen has to break up first. Okay, so let's check this out. So we're going to end up with Al. Whoops, square brackets. I don't need to get haunted by Lewis. Okay, we say, well, each aluminum loses 3 electrons, and we have 2 of them. And each oxide gains 3 electrons. So each oxide has a charge of -2, and or 2 minus, either or, I don't care. Some textbooks are fussy that way, where they're like, okay, you have to put the charge after. I don't care either way for you guys. It's all good. But we have 3 of those. And there again, there's your crisscross, right? So if I was going to do this like a crisscross style, I go 3 plus 2 minus, and then we just circle this number. Some of you prefer this, and it'll get you there if you follow the procedure. And that gets us to the chemical formula of Al2O3. Okay. And over here we got Fe2O3. There you go. And so we can see how that works and how those ionic compounds form. I hope this is helpful and you got some clarity on it. And we will attack the other ones when we return on Monday and look at the